you guys? Oh, something good? Okay, thanks for coming. Let me close the door. So by closing the door, I'm assuming you guys don't want to talk to the people outside, right? While you're in class. Okay, so today's topic is called integer programming. So it's one kind of linear programming. Okay, where are we? Yes. So if you think about it, right, we talk about linear programming, right? Linear programming means everything has to be linear, the objective function, the constraints and everything. Also, the decision variables, they are assumed to be non-negative, but can be continuous. Okay, can be like 1.5, can be 1.55, so can be continuous. Sometimes some problems require some decision variables to be integers. You know, if you're talking about number of airplanes you want to make, you have to make 1 or 2 or 3. Whether it's 2 or it is 1.8, make a huge difference, right? So there are 3 types of integer programming problems. The first type, actually there are like only 2 types, but first type is all integers. So everything is, every decision variable is integer. It's an integer. And sometimes you have the mixed integer problems. That means some variables are integers, some variables are not. Okay? And the third type is called binary, which is actually one kind of integer or integer problem. In binary problem, all variables have to be either 0 or 1. Okay? So 0 or 1. And there are lots of things we can do by using binary variables. So let's see, we can use those variables to write lots of logical constraints. They can also be used to represent the fact that sometimes you have one constraint. You know, you may have 2 constraints, right? But only one of them will hold, you know, at any time. So we're going to see those things shortly. So we do that by looking at examples. So the first example is about set covering. Okay, how about you guys take maybe like 1 minute to check out this problem. Okay, so in this example, right, there are 6 cities in a county, right, and you want to build some fire stations. Obviously, you want to build a fire station which is close to any city, right? Every city has to be, every city has to have a fire station close enough to that city, right? And you want to build, of course, minimum number of fire stations, because each fire station will cost you lots of money. So here it says that you want to make sure that at least one fire station is within 15 minutes of each city, okay? And of course, you have a map which you can tell that the distance between one city to another, right? In terms of traveling time, right? Drive time. So for example, from city 1 to city 2 takes 10 minutes to drive, all right? And from city 6 to city 3, it takes 30 minutes to drive. And of course, we have zeros, that means from city 1 to city 1, the distance is 0. Okay, so again, remember our goal is to figure out where to build fire stations, right? Such that the number of fire stations is minimized. You also want to satisfy the constraint that every city must have a fire station close enough, right? So the first step in this kind of problem is to check, the cities which are within 15-minute drive from each other. Okay, you start with city 1. So in city 1, you look at here, right? So of course, city 1 is close to city 1. City 1 is close to city 2 enough, because the threshold is 15 minutes, right? So city 3 is not close enough to city 1. So for city 1, the places, the locations which are close enough itself and city 2. So you have this, right? So let's use city 6 as an example. So city 6 is 20-minute drive from city 1, 10 minutes from city 2, 20-minute drive from city 3, and so on, right? Again, we're looking at the threshold of 15 minutes. So for city 6, the cities close enough is 2, 5, and 6, right? So that's why we have 2, 5, 6, all right? Now you want to build a fire station. You want to build fire stations, right? So to build or not is a binary decision. Either yes, either no, or no, right? So that's why you can define these decision variables, xi. So xi says if a fire station is built in city I, then xi equals 1, otherwise it's 0, right? So it is binary. And of course, this is the way to write the decision variable, right? Can you write it as xi? Of course you can, and it is better, right? Personally, I don't like this kind of notation, but it's your preference, right? Then we can write a bunch of constraints. As we said, the constraints are to ensure every city has a fire station which is close enough, right? So as we said, for city 1, right, the city 1 obviously is close enough, city 2 is the only other city which is close enough, right? So to make sure city 1 has a fire station close enough, you can, then x1 plus x2 has to be 1 or more, right? Because, how to say, this one is a fire station is built in city 1. This one says fire station is built in city 2, right? So the sum has to be 1 or more. If it's 0, that means x1 equals 0, x2 equals 0. That means city 1 does not have any fire station which is close enough, right? So similarly for city 6, right? For city 6, the cities which are close enough, or the locations where the fire stations can be built are 2, 5, 6, right? And to serve city 6, you have to have at least one fire station, either in city 2, city 5, or city 6, right? So if I want to write it, this is to ensure city 1 is covered. And of course, we want to write this constraint, xi has to be binary. So any questions here?
I think you already got the answer.
Hmm?
I think you already got the answer with the binary programming.
Okay. So you binary programming in Excel, or?
Actually, literally look, take a look. I think city 2 and city 4, you put one in each and you cover.
I have no idea what you're talking about. My mind is not quick enough today.
You put a fire hole in city 2, and you put a fire hole in city 4, and you have covered every single city.
Okay, great. Then we solve the problem. Thank you, Kyle. All right, so let's look at the second example. It's a little bit like set covering, but not exactly the same. So again, probably you take like 2 minutes. Obviously you don't want to look at the subsequent slides. Okay, just focus this one and try to think how you can formulate integer programming problem. All right. Okay, so this is a hypothetical example, as you can tell. First of all, nobody is going to use an IDP to decide which course to take in which term, right? And of course, there are lots of assumptions which are not that realistic. But we want to formulate this hypothetical situation as an IPP. Okay, IPP stands for integer programming problem, right? So you have, lots of requirements in terms of lots of constraints which guide you to select the courses, right? And you also have this kind of, input-output relationship. So if you take course 1, you will spend 10 hours per week, and you will get a grade of 12. Okay? So if you take course 5, you will spend 7 hours per week, and the grade will be 8. So suppose those are information, and how do we formulate this as an IPP? And we want to minimize the number of hours of work per week in term 2. So we have a very specific objective function. So notice the function here is not to minimize the number of hours of work per week in term 1 and term 2. You can do that, but this is not what we want. Okay? So in this example, to take a course or not is binary, right? So this is a binary situation. So we can define xi as this. If xi is 1, if course I is done in term 1, if it's not done in term 1, then it's 0. Okay? Because we have 2 terms, so we also have yi, which means if the course I is done in term 2 is 1, otherwise it's 0. Okay? Obviously xi, yi, they are related, right? So what's the relationship between xi and yi? That's right. That's right. So, again, there are many ways to formulate the same problem. But here, let's assume we want to use xi and yi. About the relationship, we can just put it in the constraints. All right. So we want to minimize the time, the number of hours per week in week 2, right? So because we have defined yi this way, then the time you will spend in term 2 will be 10x1 plus 10x2 plus 8x3. Sorry, not x but y, because y is where to take a course in term 2, right? We are interested in term 2. So it's 10y1 plus 10y2 plus 8 times y3, right? So that's why this is the relationship. This is the objective function, right? Now we have quite a few constraints. The first constraint is the number of hours per week is at most 35. So this applies to term 1 and term 2, right? Because we cannot formulate. When we decide which courses to take in term 2, we have to think about term 1 too, because term 1 and term 2 they are related, right? So that's why this is the number of hours you're going to use. You need for each week has to be less than 35, and this has to be less than 35 as well. Okay. And for each term, the GPA has to be at least 8. Okay. So this is a little bit interesting because again, if you take a course, right, that is 1, x1 is 1. If you don't take it, it's 0, right? So binary is interesting because the decision variables can only take 0 or 1, no other choices, right? So that's why on the the GPA has to be at least 8. You can write this way. So if you take only say 3 courses, okay, then this will be 3, right? This will be 3. the average has to be 8. So 8 times 3 is 24, right? So if you want the average GPA to be 8 or more, then the GPA, the sum of the GPAs will be more than 24, right? So this is very interesting. 8 times the summation of xi's, which actually force you to have, GPA 8 or more, right? So on the left-hand side, that is the sum of the the total of the grades you are going to get out of 8 courses, 8 potential courses, right? You will not take all 8 courses, but if you don't take it, it's 0, so it doesn't count. So the only courses count are the courses you take, right? So this is kind of done automatically because x1, xi can only be 0 or 1. Okay? And same thing for the second term, right? So y1 can be 1, can be 0. If it's 0, it doesn't count. If it's 1, it counts, right? Does it make sense? So that's the GPA constraint. And a course must be done only once. Okay. Yeah. So here we don't allow like fail and and then you take it, right? So as we said, the xi, yi, they are related because you take the course this term, next term you don't need to take the course, right? And then all 8 courses have to be done within 2 terms, and you can write this kind of constraints. So the summation of xi plus yi has to equal 8. And then we have other constraints like the number of courses in each term is no more than 5. It's not more than 5. Okay? So the summation of xi will be the courses you take in term 1 and in term 2 has to be 5 or less, right? And 3 or more, so similarly. So this is like a short problem, but it turns out there are many constraints you have to write. Okay? Any questions on this example? All right. So the second situation, the next situation we want to talk about is that binary variables can be used in a creative way. Okay? So here you are saying that you are a furniture company, right? You make tables, chairs, and desks. So how many to make? Those will be the decision variables. Okay? Of course, those are not binary. Those are not binary. Now you have 2 capacity constraints that depend on the material used. So you are thinking about whether to use pine or use oak. Suppose you can only use one of them, right? If you use pine, then you have only 1,500 pine trees, whatever, to make those products. Okay? But you can also choose to produce oak, right? So if you do that, the total amount of oak you have is 1,000. But suppose you assume that you can only use one material, you just want to focus on one material, you either use everything oak or everything pine, right? But of course, when you formulate the linear programming or integer programming problem, you want to maximize the profit, right? So maybe pine will give you more profit, maybe oak will give you more profit, right? You don't know. But in any case, you have 2 constraints, only one of them is going to hold, only one of them, right? So how do you model this kind of situation, this kind of problem where you have either or constraints, only one constraint, either this constraint or that constraint code are not both, right? So again, here we probably, don't give you lots of room to think about it. This is one way to do that. Okay. So you define two binary variables. You have to define at least three decision variables, but those are the two binary variables. And if you define yp, which is binary, means if you make furniture from pine is 1, is 0 if you don't. Okay. You define yo as 1 if you make furniture from oak. If you don't, it's 0, right? Now we can write the constraint in this way. So what we did is we move the numbers to the left. We move the numbers to the left. We move the numbers to the left at least. at first. Then we write the right hand side this way. So m times 1 minus yp is m times 1 minus yo. So yp, yo, as we said, that those are binary variables, right? And obviously this must be true, right? Yp plus yo has to be 1 because we can only use one material, right? We cannot use both. So why do we want to use the m? Which m here is a very large number, very large positive number. Okay, and the yp, yo, those are binary variables. So m is not decision variable. M just you give it an arbitrary large number, like say 1 million. Okay? M suppose is 1 million. And why? Because if yp equals 0 equals 1, right? Then this constraint A, yp is 1, then this is 0. The right hand side is 0, right? And then we have this, right? If this is 0, then this means the sum of those three terms is less than or equal to 200, right? So that is the original constraint for pine trees. On the other hand, if yp equals 0, then yo will be 0, right? Will be 0. If yo equals 0, that means this equals 1. The right hand side is m, right? M. So the constraint B becomes if yp equals 1, yo must be 0 because of this constraint, right? If yo equals 0, then this constraint B 0, and this becomes m plus 1000, right? Now m is a very large number, so 1 million, right? Or maybe bigger, right? So that means this constraint becomes redundant, right? So the summation of those has to be less than a very, very large number, so this becomes redundant. Redundant means it's not needed, right? So by this technique, right, you can model the either-or constraint situation. Of course, whether yp equals 1 or 0, that depends on the solution, right? To solve the problem, maybe the system find out yp equals 1 gives you higher profit than yp equals 1, right? But here we don't know yet because yp, yo, they are decision variables, right? Maybe the case you run the program yp equals 0, right? That means o equals 1, right? If yp equals 0, then constraint A becomes this, very similar, right? And this again becomes redundant. If it's redundant, that means it's not there anymore, right? It's like you can delete it, right? But constraint B is going to take effect, right? Take effect. All right. Any questions here? I will take that as a no. Okay, oftentimes we want to describe some if-then relationship, okay? So here, suppose you have 3 stocks you want to invest. Suppose one of the rules is, if you invest in stocks 1 and 2, then you must invest in stock 3, okay? And to invest or not, binary, right? So you can define like 3 binary variables, right? You define yi equals 1 if you invest in stock I, 0 otherwise. So if you invest in stock 1 and 2, you must invest in stock 3. Then you can do this. So why is that? Okay. Again, remember yi can only be 0 or 1, right? So by using this constraint, you are saying if those two, if this is 1, this is 1, then y3 has to be 1 as well, right? Now you look at here, if y1, y2 is 1, 1, then this is 2, right? So 1 plus y3 larger than or equal to 2 means y3 has to be 1 as well. And that's what we want. If y1, y2, both of them are 1, then y3 has to be 1 too. Has to be 1, right? So you can do something like this. And of course, you can write in this way as well. So on the right, y1 plus y2 minus 1. So this term will be, the right hand side will be 0 or less. If not both of them are 1, right? If you invest in only stock 1, then this is 1, this is 0, then the right hand side is 0, right? So y3 larger than or equal to 0, that's again like redundant, because we know that. We have this constraint from the very beginning, right? So if y1 equals 0, y2 equals 0, that means you don't invest in stock 1 or 2, no 2, then this is 0, 0, then the right hand side is minus 1, y3 is larger than or equal to minus 1, that's redundant, right? But anyways, this equation, this constraint captures what we want, if then, right? So sometimes we have the only if constraint. So you can invest in stock 3 only if you invest in stocks 1 and 2. Okay, so stocks 1 and 2, they are like the prerequisites of stock 3. Again, you define yi as binaries, and you can write it this way. So y3 is less than or equal to this divided by 2. Divided by 2. Then you can see if that's what you want, right? So you can only invest in stock 3. You can, but you don't have to, right? That means you want to make Y3 less than equal to 1, right? So this one basically saying that we want Y3 less than equal to 1. So Y3 can be 1 or less only if Y1 equals 1 and Y2 equals 1. Okay? So this is one way to write it. You can verify the results by checking out all the combinations, right? So if y1, y2, if both of them are 1, then it's 1 plus 1, which is 2. 2 divided by 2 is 1. So if you invest in stocks 1 and 2, the right hand side is 1. So y3 less than equal to 1 means you can invest in stock 3, but you don't have to. Right? Y3 less than equal to 1 means can be 1 even 0. You can, but you don't have to. Right? Now, if you do not invest in any of the stock, in any one of the stock, then suppose y1 is 1, y2 is 0. 1 plus 0 is 1 divided by 2, which is half, right? So y3 less than equal to half means what? So if you have y3 less than equal to 0.5, what does that tell us?
You can't invest in because it's not 1.
Then we can. Can you say that again? Sorry.
You can't invest in stock 3 because it's not equal to 1 on the right side.
That's right. If this is half, right, y3 less than equal to 0.5, that means y3 has to be 0. Because y3 can only take value 1 or 0, nothing else. Cannot take a value 0.5, right? So when y3 less than equal to 0.5, that means y3 is 0. That means you do not invest in stock 3. Okay. So again, you verify this. This is a relationship you can use to model the only if relationship. Okay. So there may be other ways around, but let me see. What are the other ways you can write this only if relationship? So, do you know? It doesn't look familiar. So I wonder why. For some reason. Maybe. How about your friend? Any other way to write the only if constraint? You don't have to do it. Yeah, what we have.
Or any number of stocks or just 2.
No, that's only constraint. So you can invest in stock 3 only if you invest in stock 1 and 2.
2y3 smaller than equal to y1 plus y2.
Yes, so that's another way. Okay, so just to make sure you get a credit, I'm going to write it down, all right? So another way to write it, equivalent, right? 2y3 So any other way to write it? Well, so what what I'm going to write down will be shocking. How about y3 less than equal to y1, y3 less than equal to y2? So instead of this, how about this? You just have two constraints. You can have two constraints, right? They are linear, so. So if either one of them is 0, then y3 has to be 0, right? And that's what we want. So y3 will be 0 if either one of the stock is not invested. So only one of the stocks is invested. Okay, so those two relationships and this relationship, those are equivalent, right? Any questions here? So for the same thing, you can use just one constraint to write it. You can also use two constraints, right? Okay. So I'm assuming you guys were nicely pleasantly surprised by this beautiful solution. Okay, now let's keep going. Something kind of similar. So suppose we have like something like capital budgeting situation, right? You have 6 projects you may or may not take on, and then suppose you want to write those relationships. You have 6 of them. Only 5 of them, or 6 of them, I forgot. Maybe only 5 now, or 6. Okay, how about you guys take 2 minutes, try to solve it. Okay, I'm going to check something.